All right, and now for our presentation. Tonight's speaker is a PhD candidate at the University of Washington, where she's part of the Behavioral Ecophysics Lab. In her current work, she studies hummingbird movement and behavior in Colombia, where she works with a wonderful field crew at Centro de Investigación Colibrí Gorazio. Sorry. Alyssa loves to come up with creative ways to share her resources or research with people, and is even working on a board game, Hummingbird Sugar Rush, to teach people the decisions hummingbirds have to make every day. Before starting her PhD, she studied fairy wrens in Australia, owls in Canada, storm petrels in the Azores, Kirtland's warblers in Michigan, and hummingbirds in Arizona, plus songbirds in Missouri. So tonight, she'll be sharing how cutting-edge technologies help answer questions about what is a day in the life of a hummingbird entail. So please join me in welcoming Alyssa Sargent as she presents Hitchhiking on Hummingbirds using Tiny Tech.
Thank you. All right, thank you for that introduction. Let me know if at any point you can't hear me, just, give me a wave or something. So my name is Alyssa. I'm going to be talking to you about the tiny tech that we use to hitchhike on hummingbirds. And yes, I am a PhD candidate at the University of Washington. I did get asked at the dinner, how far am I into my PhD? I am now a 5th year, so I'm getting in there. I'm hoping to wrap up soon. So I wanted to just give a little bit of an idea about the inspiration behind this project, what led to the idea of working with technology. And so, as was mentioned in my brief bio, I have done a lot of work in various places around the world studying birds, so I've gotten the pleasure and the fortune of working with birds out in Australia. I've worked with birds in Canada, so primarily owls out there. I've worked with birds in the Azores, so songbirds. I worked with a lot of birds, and it's been really cool. It's been a lot of fun. It was a very formative experience. And maybe you all already have a good sense of this, but something that was surprising to me was the fact that a lot of this work is actually pretty manual. You have a pair of binoculars, you are running around after the birds, you're trying to see what they're doing. The bird moves, you're running after it, you're trying not to lose it. And it was very cool, but it sparked for me an interest in, how can we optimize this process a little more? How can we start working with technology to make this a bit more efficient? So that was the inspiration behind, let's use field electronics to start working with birds and learn more about them. And there's a whole lot of research that's being done, obviously, on this. And you guys have talked about Lotus tags a lot. My systems are similar, and I'll talk about that. But during this time, I was also really interested. So all that work that I did, that was right after I finished undergrad. So I was doing a couple of years as the field tech, being sort of nomadic, moving from place to place. And I was very interested in working with hummingbirds at this point. I was thinking, I want to study hummingbirds for my PhD. I got to find a lab. I was emailing so many people, dozens of people, trying to find someone. Eventually, I did find my current supervisor, Alejo Guevara. So we work at the University of Washington. And now we work with hummingbirds. And it's really cool. So I will talk a little bit more about that soon, but just to give you a sense of where we work down in Colombia. So this is going to zoom in on our field station. So we work at Centro de Investigación Colibrí Gorazul. So this is our site. It is named after the indigo capped hummingbird, which is endemic, very cute. Unfortunately, I don't have any pictures of them in this talk. I should have. I'll do that next time. So this is where we work. It's a great place for birds. I mean, hummingbirds especially. We've got thousands of hummingbirds there. It's really cool. You'll see lots of footage from where I work momentarily. But I want to return to that whole question of, why hummingbirds? What is so cool about hummingbirds? What got me hooked? And for starters, right, there's an insane amount of variation when it comes to hummingbirds. They are cool. There's over, I think now the official number, last I heard, was 365 species of hummingbirds. So there are a lot of hummingbirds out there, and you can see that there's a lot of variation in how they look. We've got the sickle-bill hummingbird in the middle, really curved bill. If you see, I've got that one tattooed on me. So you might see it waving around on my hand as I gesticulate wildly. We've also got hummingbirds with crazy bills, like the sword-bill. That's the one next to the sickle-bill there. It's got a bill longer than its body. That's the only bird in the world for which that's the case. We've got plover crests on the top right and the bottom left here. These birds just have absolutely crazy crests. We've got coquettes. That's the one in the top with the very orange feathers coming out its cheek. You know, we've got a lot of variation when it comes to hummingbirds, and they are cool. And yeah, I've already spent longer on this slide than I meant to, just because I'm so excited. But anyway, not only that, but hummingbirds are very extreme birds as well. They have crazy abilities that we just can't even fathom. And I thought, what better way to illustrate the extreme measures that hummingbirds will take than by doing a little face-off between them and arguably one of the most extreme humans alive today, Dwayne "The Rock" Johnson. So I'm going to do a couple of rounds and we'll see who comes out on top. I have no doubt you already know where this slide is going to go. Let's walk through it anyway. Okay, so first round is speed. Now, the fastest man in the world, Usain Bolt, tops out at around 27, 28 miles per hour. So that is very fast for a human. Hummingbirds can fly at forward speeds of around 31 miles per hour. So even compared to Usain Bolt running as fast as he can, he's not going to hold a candle to a hummingbird. And for that matter, unfortunately, The Rock is not going to either. When a hummingbird is diving, also they can dive at around 61 miles per hour. So we're going to give a point to our bird here. Okay. Metabolism. Okay, now, if Dwayne "The Rock" Johnson were to burn as much energy in a day as a broad-billed hummingbird, that's the hummingbird that you can see in the photograph there, he would need to eat around 6,110 chicken nuggets. Yeah. Or maybe 193 12-inch pizzas if you want to put it into terms of pizza. So we can assume, right, that even on a cheat day, Dwayne "The Rock" Johnson's not going to be eating quite that much. So I'm going to give another point to our bird. Okay, acceleration. Now, hummingbirds can accelerate at around 10 G. So that's a rate that is pretty comparable to what a fighter jet pilot is experiencing. So we're talking very, very extreme acceleration. Now, Usain Bolt can accelerate around 8 to 10 meters per second. And if we put that in terms of hummingbirds, hummingbirds can accelerate at roughly 98 meters per second. So again, I'm going to give a point to our bird. The trend continues. Okay, now I want to talk about movement. Now this is an interesting one. We don't have great numbers for how much distance a hummingbird will cover in a day when they're migrating. So you'd have to have very, very tiny technology that we now have, and I'll talk about that, but up until now we haven't had it, so we don't have numbers on that yet. But once you start putting these tiny tags on these birds and you start tracking them with MODIS towers, we can get a better sense for how much ground these particularly North American bee hummingbirds are covering in a day. But some scientists have estimated that hummingbirds can cover around 19.9 miles in a day when they're migrating up to North America. And that is around it's more than 400,000 body lengths in one day. So we're talking a lot of distance. Now, the most distance covered by a human in 24 hours was, I gotta check my slide for my number, I have it in my notes, it was 198.6 miles. And so that is a lot. But if we put it into body length, so that man was 5'11", that's around, let's see, 177,000 body lengths. So even still, if we put it into terms of body lengths, hummingbirds are coming out way on top, more than 200,000 body lengths more than a human can cover in one day. And not to mention, I think that the numbers are going to be higher once we start getting those MODIS tags out there. Okay, Another point for our bird. Okay, last round is reflexes. Now, the fastest thing that we can do, maybe you think it was blinking. We can blink maybe, what, I don't know, 2, 3 times, 4 times in a second if you're really fast. I can maybe do 2. And that takes around, so a blink takes around 150 milliseconds. Whereas actually the fastest thing that we can truly do is, according to some scientists, snap our fingers. That takes around 7 milliseconds. So snap your fingers once takes around 7 milliseconds. Now, hummingbirds, on the other hand, can flap their wings around 135 times in 1 second. Now, that is an absolute maximum. That's when they're doing a breeding display, so it's a very extreme moment. But that's been recorded. And so if you break that down, actually, that is 7 milliseconds per flap. So we are about equal, but I will say that a hummingbird can do that 135 times in 1 second, whereas we can snap maybe 1 time in a second, right? So I'm gonna give another point to our bird. And I'm gonna crown them the winner. So, sorry, Elaine, better luck next time. Okay. Now, I want to put into practical terms some of this stuff that we were talking about, right? Hummingbirds are very fast. They are also, of course, the world's smallest birds. And this bird in particular is a really good example for that. You can see, so this was a bird we caught in Ecuador. This is the striped-throated hermit. And you can see my colleague is holding the bird there. And you can see that the bird is about the size of that upper knuckle of her thumb. You know, the entire body, the head. The only thing that you're really not seeing in that photograph is its tail, which is very long. But I mean, that's the whole bird, basically, right there. That bird weighed 2.17 grams, which is about as much as 2 M&Ms. So we're talking very small birds, very fast birds. Now you take that bird and you put it into a complex environment like a tropical rainforest, right, which is where a lot of hummingbirds live. You've got a lot of vegetation on a lot of levels. It becomes really difficult. Okay, so now we're thinking, let's try to study this bird in the wild the way that we usually do, right? Let's run around after it with binoculars. You are probably going to have a very hard time with that. So it's sort of like trying to find a needle in a haystack. So that's kind of where my research comes in, and that's why we have a lot of things that we still don't know about hummingbirds. And we don't have a great understanding of how are they surviving on the daily, you know, what are they doing that's different from each other to survive? Okay, now I want to show you, this is one of the feeders at our station. So this gives you a good sense for the kind of numbers that we're getting, the sheer variety of hummingbirds that we have. We've got something like 20 species that can visit at this station. And you can see it's very chaotic, right? There's a lot happening. There's some birds that are very aggressive, they are fighting each other. There are other birds that are much more timid and they're waiting for things to clear out a little bit. They're gonna wait until there's a quiet moment and then they'll sneak in, like this mango right now. And then more birds are gonna come in and start to get aggressive, and yeah, so there's a lot happening. There's a lot of behavioral variation that we're seeing. And so something that I want you to keep in mind as we go on is that hummingbirds have very different strategies to survive. And strategy is a key word, so I want you to keep that in mind because I'm going to be talking about strategies a lot. So strategies are the tactics employed by different species when they're adapting to different environmental or other conditions. So I want to take this concept and I want to move it to a natural environment, right? Okay, so we're not talking about just feeders now, we're talking about flowers too. And something that's also worth keeping in mind is that flowers don't all have the same strategy either. Flowers have different reproductive strategies. We can see that in the way that these flowers are spaced out here in this illustrated example that I have. So you can see, right, we've got these heliconias. Those are those red lobster claw style flowers in the middle. They're spaced out very far apart. There are others that are in these clumps like these Elianthus and Calyandra flowers. Those are the pink ones, and the red sort of pom-pom flowers. So you can see that there's a lot of variation in how these flowers are actually spread across the landscape. And so the hummingbird then comes to a point of decision making, right? Should I stay? So should I be staying at these clumps of flowers? Should I go? Should I be traveling across to these dispersed heliconias? Or should I do something else entirely, something else in between? So we do see that the birds are sort of stratifying across these lines. So The birds that stay we consider to be territorialists. So these are birds like the sparkling violet ear. Got this one on my other wrist. That's this one here. So this is a very territorial bird. They are birds that tend to defend resources. So if you have a feeder at your house or wherever you live, or if you've seen birds at feeders, you will know this. Birds are aggressive. Hummingbirds are very aggressive birds. They defend resources. They will fight each other over food all the time. So these birds in particular do that. We also tend to see that these birds have larger body sizes, right? You know, you think about even across all animals, across humans, if you're bigger, you have a much easier time fighting a person or another individual who is smaller. So these birds we tend to see are pretty big. They also tend to have a little bit more generalized or weaponized bills. So thinking about, it's more of a jack of all trades kind of bill. It's not super long, super curved. It sort of fits with a greater variety of flowers. We also tend to see with those weaponizations bills that are very, very dagger-like at the tips, or bills that are even serrated at the tips. And they use this to stab each other or to pluck out each other's feathers. So it's kind of like if you think of a steak knife or something with those little serrations on it. That's what hummingbird bills can look like up close. So we also tend to see brighter colors with these, so they use these to display to each other, whether or not it's to a rival or to a mate, trying to impress them. So we tend to see that these birds are very flashy. Now, I want to show you what a fight will look like up close. This is a black-throated mango. This is a female, and she notices a black-throated male, and she's like, you know what, I'm going to ruin his day. So she does. He wasn't doing anything wrong, he wasn't bothering anyone, but she decided, you know what, I want to kick this guy out, and she did. So this is very, very common behavior for hummingbirds. We see this a lot at feeders, we see this at flowers. Hummingbirds are often not quite as nice as they seem at first blush. So I also like this video just because it's funny. This is another bird avoiding a fight. You can see his pursuer sort of gliding past in the background. So this is a rufous-tailed hummingbird getting attacked by an indigo-capped. Oh, that is the indigo-capped hummingbird that the station is named after. You can see him sort of flying past for a second. Okay. So how do we actually study this sort of monopolization of resources, right? That's what territoriality is all about. It's about making sure that you have the resource and nobody else does. So you're fighting off all those other birds. And one way that we can study this is by using essentially what is microchipping technology. So if you've ever microchipped your pet, you might know what I'm talking about. It's a very, very tiny tag, smaller than a grain of rice, that you put under the skin. And essentially, we have these high-tech antennas that we set up at the feeders, and it will register when a microchipped hummingbird arrives at that feeder. So we can see, okay, the little thing is lighting up, and my colleague Anna is saying, ah, yes, there's our bird, in a completely candid and not at all staged video. So essentially these antennas are really cool because it gives you a good sense of, okay, well, who's visiting my feeder? How long are they visiting it? When do they leave? And basically, without this technology, right, maybe you've seen birds at a feeder or at your own feeder and you wonder, okay, well, I don't know if it's the same bird every time. Maybe you think it is. Maybe you wonder if there's more than one. Having this technology really lets you look into the science behind that and looking at the behavior. And so actually, I have some cool plots here. So this is from Jay Falk, who actually gave a talk with you all, I think it was maybe 2 years ago. So Jay Falk is a former postdoc in our lab. So when he came to talk to all of you, I expect he was probably talking about white-necked Jacobins, which is the species that he was working with. And this is what all this data is as well. I don't know if he had time to get into this with you. I think this analysis is fairly new. I was helping him out with this. But essentially, he had a grid of all these feeders in Panama that were equipped with these RFID antennas. So the RFID is radio frequency identification technology. That's the little microchipping. Anyway, so he had all these feeders that were set up with this special tag. And you can essentially see how all of these different strategies play out, right? So in the top left, we can see Arizbell, and you can see, hopefully, that bird visited. If you take a look at the number underneath those feeders that the bird was visiting, it visited that one feeder 138 times, and it visited another feeder 1 time. So there's a lot of territoriality going on at that feeder, right? That bird is very much defending that feeder from other birds. And we've got, for instance, Floor, who has 42 visits to that one central feeder, and then a bunch of random visits to a couple other feeders that bird maybe doesn't consider as important, but probably being a little bit territorial, but maybe a little bit less than Arabelle. And then you've got Joseph on the far right, who is just being completely insane, just doing whatever, right? So there's a lot happening there. But then you can also see that Joseph is underneath on the bottom right as well, and you can see that the strategy has changed a lot, and that's just 2 days. So we can see that not only do these birds have different strategies, but the strategies will change over time as well. So that is from a paper that will be coming out soon, hopefully, if you're interested in learning more. Okay, now we do tend to see birds that go as well, and we consider these birds to be what we call trapliners. And that term was coined by a scientist who saw this behavior and thought, it's kind of like a fur trapper checking their line of traps. So essentially it's a bird or another animal, could be a bee for instance, that will be visiting these dispersed resources in sort of a set circuit. So it will be going across, saying, okay, here's my first trap, here's my second, here's my third, and so on, and sort of just going around and making their way. And so the white-tipped sicklebill, again, one of my favorites, is a really good example of traplining. And we tend to see that these birds don't defend resources. They are not the ones that we see staking out a certain resource and fighting off all the other birds. They tend to be birds that will commute long distances between these resources. And we tend to see that they have smaller body sizes because they're commuting a lot, right? You don't want to have a ton of weight with you as you're moving really far across the landscape. I will say the white-tipped sicklebill is an interesting exception to that rule. They're really big for hummingbirds. And when I say really big, I mean like 10 grams, which weighs about as much as an Oreo. Okay, we also tend to see that these birds have specialized bills. So really curved bills, for instance, to fit with certain flowers that they've co-evolved with over a really long time. And so the sicklebill, of course, is a very good example of that because they are extremely specialized. They're what we call extreme specialists. Okay, and we also tend to see duller colors. These birds aren't super flashy. They tend to camouflage a little bit more. Okay, now how do we study this going behavior? And one of the ways that we do it is through a number of tracking devices. So on the left-hand side here, we have what's called an accelerometer. It's measuring acceleration. And in the middle and on the far right, we have radio tracking devices, which are very similar. They are actually MODIS compatible. So for those of you who know about MODIS, it sounds like all of you do. That's what that sort of technology is like. Mine is a little bit different, but you could essentially track them with MODIS towers as well. So these are some of the kinds of technology that we use, and the radio tracking devices, essentially, they will emit a radio signal to different antennas that we have set up across the site. So we'll have different antennas, and then those will receive the signal, and you can essentially pinpoint where the bird is going, and you can create really cool maps as to where the birds have been moving. And I want to show you what some of those maps will look like. So these are some maps from our birds. I'm actually going to click on this link so that we can take a look. Okay, so this is our map. So to orient you, all of these yellow points, these are our receivers. So it's not quite like MODIS in the sense that you have really big towers spaced super far apart. These are much smaller antennas, and they're spaced, this is around 600 by 600 meters. So this is our grid, and if the bird goes too far outside of that, super far, then we don't get any information. So that's the kind of radio tracking that we're working with here. And all of these red points, these are our feeders at the station. We have around 20 feeders set up at all times, basically, constantly being filled. We use about 50 kilograms of sugar every month. And I don't know how much that is in pounds, but it's a lot. Yeah, over 100 pounds of sugar. Okay, now I want to show you what some of these different maps can look like. So this is Flynn, which actually, this is very interesting. this is a side note, this was a male like female. So Jay Falk, when he was here, he was telling you about how white-necked Jacobins, sometimes the females will look like males. This was a bird that we thought was a male, and then later we saw her on a nest, and we said, oh, that was a female. Because only the females will do any nesting behavior with hummingbirds. Okay, and this is Gollum, and you can see what we were watching and what we were inspired by, depending on what the names of the birds are at the time. We've got Neo. So, I mean, the point of me showing you these maps is to show you just how much diversity we have in terms of the movement and the space use. So all of these maps that we have are from black-throated mangoes and birds that we thought were males. For the most part, I assume that they are males, although Flynn did sneak in there as a female. And then, you know, this is Apollo. So we can see a very, very small amount of space used by Apollo, whereas Connor's got sort of a... Oh, crap. Okay, sorry. Okay, let me stop sharing my PowerPoint briefly, and then we will get to the link. Okay. There we go. Sorry about that. Okay, let me back up. So yes, the yellow points are the receivers, the red points are the feeders. Okay, and then we've got, okay, Flynn is this yellow map here. I'm gonna close out Neo. Neo kind of swabs out everybody. Okay, so these are some examples, right? So we've got Flynn, who's our secret female. We've got Gollum, which is the black map. And then we've got Neo, which was really massive. So this bird was covering a really huge amount of space. And actually, this was over a pretty short amount of time. I think it was only a few days. So within this species and within this sex, we can see a lot of variation. And then Apollo's barely moving at all by comparison. And then Connor's sort of a middling amount of space use. I'll remove Neo so that we can see a bit better what's going on. So this is just to showcase the sheer amount of variety that you can get when it comes to hummingbird movement. And I'm going to return to our slides so that we can see the next one, which I'm really excited to show you all. Okay. So now I'm going to show you something that is very similar but a little bit different. So just to orient you all again, these yellow points are our receivers, so those are our antennas, and then our red points are our feeders. And this is going to be Aragorn's map, and I'm going to animate the movement. So this is going to show you what the movement looks like over the course of time. And so the blue will be Aragorn's movement. And I want to point your attention to, we've got the date and the time at the top there, okay?
Where is the blue? I'm sorry.
It hasn't shown up yet. It will show up momentarily, yes. Okay, so here's our blue point, right? Okay, so this is the movement over the course of a day. Okay, now the bird is roosting. This is nighttime, okay? And the bird is going to wake up and go crazy. And then, okay, roosting again. So we're moving really fast through the days, but you can see that this bird is sleeping in the same place every night. And then during the day, it is moving a lot. Occasionally in the mornings, we'll start to see that the bird maybe will have a slower morning. It'll go out a little bit more slowly, like right now. And then once it gets some energy, it'll start moving really quick. So this is a good example of the kind of data that we can get from these different movement, essentially pieces of equipment. So what we can see here is that this bird has some sort of patterns to its behavior, but also it is kind of going all over the place. So it's possible that in the mornings, it's doing a little bit more searching, it's kind of looking around for resources, and then as the days go on, either it is visiting resources that it knows, or possibly there's other farms that have feeders set up as well, so it's possible it's visiting those. Maybe it's visiting certain flowers it knows, so it could be some sort of trap lining happening here. Yeah, so that's really cool, really exciting, and once I have a little bit more time, I'm going to start to animate all of the birds moving at once so we can see the true chaos. Yes, maybe a little bit overwhelming. Yeah. Is there a question?
Yes. See how right now, is it even moving during its sleep?
No, I think it's just there's a little bit of error associated with the different points. So that's probably why it looks like it's moving around, but it's just that the points are,
Okay.
Yeah.
And it never visited the feeders.
Yeah, it's very interesting. This is only a handful of days, and these are the first couple of days after the bird got tagged. So it's probably rightfully a little bit wary of coming back to the farm. It's like, I don't trust you guys. So the Aragorn did come back after this, period of time to the feeders. But yes, in those initial first days, he was a little bit wary of all of us, a little bit distrustful. So it's really cool what you can get with this kind of movement stuff. There was something else I wanted to say on this slide, but I don't quite recall what it was. So if it comes back to me as I go on, I will return to that point.
Excuse me. Also, there's the slowness in the morning before he gets some energy.
Yeah.
And then, I can't watch the clock at the same time, but there's a slowness. Is that another slowness in the days of that hot time of that?
Yes, we do tend to see that during the day. So with hummingbirds, we tend to see two peaks of activity. It tends to be in the morning and then in the evening. So during the day, when it's noon and it's very hot, the birds are, they're usually laying pretty low. Mm-hmm. So it's likely that that's that other slow period that you're seeing. Yeah, it's a really good point. Okay. And feel free if you have any more points or questions you want to hit me up with as we go. Feel free. I'm happy to do it that way. That's always fun.
What do you know about the roost site that it keeps going back to?
Yeah, really interesting. I'm pretty sure that that's a farm where two brothers lived. They had a lot of flowering plants. Unfortunately, there was just a new farm that came in and they cut down a lot of those trees. So yeah, that was over the past summer actually. So we're all very disappointed and annoyed whenever we look over at that farm. Yeah, so I think that that's where that was. But it's very interesting because you wouldn't think that a hummingbird would necessarily need to roost or want to roost in the same place every night. They just sleep on a branch. So it's interesting that they go back repeatedly to the same place. Unless this was a nesting bird, but that's very unlikely. Because we check all the birds when we get them to see if they've got a brood patch or anything, any indication that they're breeding. So I don't think that this bird was breeding, but it is hard to be sure. But it's very interesting. Okay, so I want to move on to the accelerometers and show you a little bit different data that we can get. So this is the kind of data you can get with an accelerometer. So this accelerometer is measuring acceleration across 3 axes, not just one. So we're getting acceleration across the X, Y, and Z axes. So essentially we're looking at, okay, from any direction is the bird accelerating. And it's really important to do that because hummingbirds can fly in any direction. They can fly forwards, backwards, upside down, sideways. I've seen them do it. They can do it all. So what's really cool about this is you can get a better sense for what the bird is doing across the day. So with this kind of data, you can see, okay, is the bird flying? Is it perching? Because with this other data that we have, right, this movement data, we can get a good sense for, okay, is the bird, moving slowly, or we can get basically a sense for, okay, is the bird kind of sitting around or is it flying like crazy? But if the bird is hovering or anything, we have no idea. So with this kind of technology, we can even look at if the bird is hovering or not, which is really cool. So essentially you see that there are these sort of dead periods, right, where there's not much change across any of the axes. This is when the bird is perching. And then in these other periods where we've got these massive amounts of differentiation, that's when the bird is flying. So it's a really interesting technology because it lets us see whether or not the bird is, but we can basically look at what we call time budgets, where we break down all of the behavior a bird has over the course of a day. So we can say, okay, how long did this bird spend perching? How long did this bird spend preening? I'm not sure if we'll be able to get preening data from this, but essentially you can get a lot of information. We have accelerometers that are really sensitive as well, so we can even look at wing flapping frequency, which is something that would be really exciting if we can do that next season. Speaking of next season, I want to give you a little bit of a sneak peek as to some of the stuff we're going to do later. This is not my photograph. This is essentially a new kind of tag that we're going to be using. I don't work with butterflies, but we're going to be using this exact kind of tag with hummingbirds. So this is a tag that weighs 60 milligrams, which is about as much as a half of an M&M. a little bit more actually than half of an M&M. So these are very, very tiny tags. I wish I brought one, but I didn't think of it. Also, all my tags are in Colombia at the moment, but even if I held it up, you wouldn't even be able to see it because it's that small. I mean, you can see on the butterfly it is quite tiny. So with this kind of tag, you can actually track anything. You can tag a 2-gram hummingbird and still be under the weight capacity that you need to be under. And that is really exciting. So we're going to use these tags to essentially track all the hummingbirds at the station. Well, all the ones we can, all the species, which is really cool because we've got birds all the way down to wood stars, which are around 2.5 grams. So we're very excited. Okay. Now I want to show you some other tech that we're going to be using. So this is what we call a wind tunnel. This is not tiny. This is a very big piece of equipment. It's about the length of maybe like the length from this end chair to the other end chair. So it's very big. But essentially you have these massive fans and you can create a lot of wind and you can adjust the wind to the speed that you want. And you can see how fast a bird can fly. So essentially you have this plexiglass chamber in the middle and you've got the wind going at the speed you want and you can see how the bird does. And so this is a hermit, this is a green hermit flying at 7.5 meters per second, which is, as far as we know, this is the first hermit ever tested in a wind tunnel, which is very exciting, just on its own, before we even analyze the data. But yeah, essentially we can see how fast the birds can flap their wings, how fast they can manage in terms of wind speed. We can see what their wing kinematics are like as they're flying at these different speeds. So we can see, you know, essentially at this speed, the hummingbirds have to have their body really low, right? They have to be almost horizontal to manage to fly at these speeds. And whereas, you know, when a bird is flying at 0 or 2.5 meters per second, they've got their body much more upright. So we're looking at the kinematics of all these different variables across a lot of different species. Okay, now I want to show you one more category, our in-between category, and these are our filchers, what we call. They're essentially these sneaky little birds like the magenta-throated woodstar. They're very tiny. Woodstars are very, very small hummingbirds, around 2.5 grams. And they are generally birds that don't hold a territory, but they're also not covering massive distances. They're birds that really just will dip into a territory, steal a little nectar, and then dip out. So they're just trying to go under the radar and avoid detection. So with these birds, we tend to see short generalist bills. So they aren't, again, super co-evolved. They're also not super, they don't have quite long bills as most of the territorialists, just by dint of being so tiny. Their bills are a little bit smaller. We also tend to see that they have smaller body sizes. So these birds just can't really hold up in a fight. So they tend to be very small, and they use this sort of tininess for sneaking. And again, territory parasitism, that's another term that we use. They're just stealing nectar from another bird's territory. And we tend to see brighter colors, and these birds mostly used to display to mates or to a fellow rival of, you know, their own species or someone similarly sized. Okay, and I want to show you what these birds look like. This is not my video. It's also a little bit grainy, but this is just an example of how they look when they're flying. So you can see just how tiny they are. Well, hopefully you can get that sense. To me, it's very clear that they're small just because of the proportions of the body. But yeah, they are essentially quite small. And these guys are generally, you can see him looking around kind of warily. He's just making sure nobody, you know, kicks him out. Yeah. Okay. Now, I want to talk about the game that I've been working on. So Hummingbird Sugar Rush, that was mentioned briefly in my little background. And so this is basically a board game that I've been working on to teach people about all of this stuff that we just talked about, all these different species that we just featured, and the different strategies that these birds have. So I want to show you just some of the process. We've done quite a bit. You can see in the beginning we had little like toy dinosaurs we were using to move around as our fake hummingbirds, which is close enough. We had, you know, you can see as we went on, we added territories, and then I started hand painting all the player pieces. So these are all museum specimen printed heads. So these are all 3D scans of museum specimens. So these are all life-size. So you can see, just in this photograph here alone, the size difference in all of these species is massive. So we've got our sicklebill, as I said, very big for a hummingbird, our wood star, and then our violet ear. And you can see, even just in the photograph, that there is that very, very fine tip to the violet ear's bill. That is the weaponized bill. They use that sort of dagger to stab each other. Okay, now in the game, and then I wanted to point out that we do have an actual official board game now. I'm still adding to it, but we've got a box, which is cool. And we actually have a Spanish version now, so everything is fully translated into Spanish as well, which is very fun. And so in the game, you play as one of the 3 species, and you have different strengths and weaknesses depending on what kind of hummingbird you are. And you can see that even on some of the cards, you can see a little bit of that. So if you're a violet ear, you're good at fighting, but you're not maybe so good at moving long distances, whereas the sicklebill, for instance, vice versa, you're not very good at fighting, but you are very good at commuting. And then in the middle, we have our filcher, who is able to move in any direction because they're very sneaky, but they're also not very good at fighting either. So you've got basically these different strengths and weaknesses that you're playing with as you go, and your goal is to collect as much energy, which are those little gemstone sort of pieces at the top, from the flowers across the board. And you're trying to account for the different strengths and weaknesses of all the other hummingbirds as you go. And your goal is to, get as much energy as you can without getting fought by another hummingbird, or kicked out of a territory, or potentially losing energy to a sneaky filcher. Now I want to show you just a couple of pictures of the game in action. So the functional morphology class at the University of Washington were some of my guinea pigs for testing out this game. They were very willing, which was great. And then we also have what we call a chaos edition of the game, which is actually very aptly named. Essentially the students play as the different hummingbirds, and they run around outside. It is very chaotic. But yeah, essentially it is the same concepts, just all applied in person. And we did this down in Colombia, so again, everything's been translated into Spanish, so we've been running it with Spanish schools, and now the goal is to start shifting and expanding the reach of this game across Colombia, but also Seattle and other places too if we can. So yeah, if you want to collaborate, if you work at school or something, hit me up, we can talk. Okay. Now I think this is my last real slide. I want the takeaway from this talk to be that hummingbirds are cool, which I'm sure you already all knew and agree, but I wanted to just highlight that. But B, that hummingbirds have different strategies to survive. Not all hummingbirds are the same. They often behave very, very differently. And so if you take anything from that talk, I hope that will be one of the things that you walk away with. And I'm happy to take any questions that you might have.
What are some of the major questions that your research is going to answer?
That's a great question. My primary interest is what is the difference in, I should have maybe mentioned that. One of my primary interests is what is the difference in terms of movement that we see for these birds with different foraging strategies. So birds that are classically considered to be territorialists versus trapliners, do we tend to see that the movement actually plays out the way that we expect it to? Because in all honesty, we talk, across hummingbird biologists, we talk a lot about traplining, but there's really very little direct evidence to support traplining. It's just that somebody sees a bird and a flower around the same time every day and they say, traplining. But without the movement part, without tracking, you really don't know. Yeah, so great question. Yeah.
Do you ever map onto your tracking maps positions of actual flowers?
Yeah, that was...
Another question I have is, presumably the flowers that they're visiting have a very long season over which they're flowering and producing nectar. Otherwise, unlike here, where it's very seasonal,
Right.
they're gone.
Yeah.
Are they long-lived flowers?
Some of them, it depends a lot. So we have some flowers that are longer lived, like the heliconias, for instance, they tend to be around a bit longer. But a lot of them are very ephemeral as well. It's just that we've got a lot of flowers that will come take their place as the ones die, yeah. So that's a great question. I have not been doing that in my work. It is a massive amount of effort to map all the flowers across that amount of time. Because you'd need a massive team of people to do a 600 by 600 meter grid and try to find all the flowers and keep track of them as they're dying. So it'd be very, very challenging. It would be a great project.
They also go to tree flowers, so
yes,
so
Yes.
verticals. Okay.
yes, yeah. So we're working across multiple stories.
Okay.
Yeah, so it's a great question, and it would be excellent to do, but it's a little bit outside of my capabilities, I think. Yeah.
Along that same line, wouldn't it, if you were doing something like that, wouldn't it serve the purpose to actually put some kind of technology on the flower?
Yes, that would be great. I would love to do that.
Yeah, and so then for each flower, or somehow be able to track what birds come to it, at what time of day, you know, that
Yes.
kind of thing. But just have it on one, you know, the flower.
Right. Yes, so that would be super cool to do. So essentially, we've thought about doing that. You would have to use that sort of microchipping antenna technology I talked about before. You need essentially an antenna on every flower. So it becomes very, very expensive, very fast to do that. Because the tracking technology that I use, right, so we were talking about these sorts of maps that I've got. There is a lot of error still associated with each of these localization estimates. Not quite as much as you would get with MODIS, for instance, because MODIS is very, we're talking big towers, and you're just sort of, okay, we've pinged it, it's somewhere in this 1 kilometer or 2 kilometer radius. My tags are more precise than that, but there is a lot of error, so we don't know exactly, okay, the bird was at this flower. Hopefully we can get to a point where it is that precise, but the technology just isn't there yet. So I think the question that you're asking is a great one, and we would love to do it, but it is very expensive, so it's a bit cost prohibitive to do it that way. Yeah, you can maybe do it at select flowers, like if you wanted to work with trapliners, for instance, though. And we've thought about that. And there's a lot more I can say about that if you want to follow up and ask more questions. Yeah.
Alyssa, how much do these things cost?
Great
And how long do they
question.
last? And do you recapture the birds and recover them, or not?
Yes, great question. So these tags, all right, so let's go back to this video. So the tags that we were using in the past were a bit shorter lived and they were bigger. The new tags that we're talking about, okay, actually I should have gone ahead. So the new tags that I'm going to be working with, these ones, these are, again, very tiny. They also last, so it depends on what you set the beep rate at, right? So how often you want data. Oh, that was the thing I wanted to mention on my other slide. Okay, well, I can come back to that. But yeah, so if you have your tag beeping once every 3 seconds, essentially, let's say that hypothetically as an example. If you have a data point every 3 seconds, the tag will last 49 days. So you can get quite a bit of mileage out of it. For a tag that small, that's very state-of-the-art. And they last, yeah, so I talked about how long they last. They cost, I think those tags cost $112 or something, yeah? So for tags, actually, that's very cheap. But yeah, compared to a GPS tag, for instance, which is very, very expensive, which is the gold standard. If we could use GPS, we would, but they're too big at the moment. And then your question was, how do you recover it, correct?
Do you recover them? Yeah.
Yes. So with those tags, we wouldn't need to recover it because they'll be transmitting data just automatically. That's the nice thing about using this sort of automated system. Everything it's just sending the data on its own. It's not storing the data on the tag, which is very nice. For instance, the accelerometers we use, those store the data, so you have to collect the tag. So you have to recapture the bird. With these ones, we'll glue it to the bird so that the bird doesn't have to wear a harness or anything, and then we'll just collect the data automatically. So you've got a little bit of electronic waste, but considering that the tag is like this big, I think it's better than having a harness on the bird and having to have the bird wear the tag potentially its whole life. Yeah. Yeah.
But then if you don't, I'm sorry,
Yeah.
I'm just thinking if you don't recover the tag, and, you know, it goes out of its
Mhm.
life, it dies out.
Yeah.
But you don't recover it, then the bird has this tag on it the rest of its life, doing nothing.
To the molts.
Right, yeah, well, you mean if you're using a harness? Sorry?
Right, what, right, if you say that you don't have to recover the tags.
Right, so we glue the tag and then the glue will just wear out and it'll
Oh,
fall off.
glue
Or
works.
or as someone pointed out, if the bird will molt, the tag will just like be sort of pushed off. Yeah, yeah,
Okay.
great question.
We unfortunately have way more questions than we have time for, so
Yeah.
if we put your email address in like the next
Yeah.
newsletter.
Sounds great.
We just have to make sure that people have a way to ask you
Yes.
more questions, because there's so much interest here tonight that I don't like closing it off, but,
Right. No, absolutely, that sounds great.
well, thank you
Yeah,
so
no
much.
worries.
This is so